Hello, so this is my review of lecture 23 of diagonalizing matrix. So in this part I will discuss about the first 3 points here. So this is actually the heart of this lecture. This formula right here is the heart, is the most important part, the most crucial thing in this lecture. So that is called the diagonalizing. So what is this? Where does it come from? So we learned from the previous lecture that a matrix times a vector equal to a scalar value times that very vector. So these are the same thing. So these are called the eigenvector and these are called the eigenvalues. So let me just write that evol eigenvalue and this is the eigenvector. Okay, so those two, we learned this in the previous lecture, and we learned that there could be a multiple eigenvector and each eigenvector has a corresponding eigenvalue. So what if I write them in some kind of matrix form? So let's say this is the eigenvector number 1. Let's say I have a 3 eigenvector. So what will I get? So if I multiply A times the first eigenvector, then I will have this lambda 1 times x1, right? So we can also write these in the matrix form. So x1 multiplied by the lambda 1. So I can write it, so because this is a column, so I need a constant to multiply the column, and for that thing I need a matrix on the left of this eigenvector matrix, and this will be my eigenvalue of 1. And the same thing happened here, eigenvalue of 2 and eigenvalue of 3. Okay, and the rest of it are 0 and 0. So this is just like multiplying each column by some coefficient, that coefficient that happens to be the eigenvalue. So we have this multiplied by this guy and this guy multiplied by this guy, and that exactly match what we have here. So A times this guy is this blue guy, and the one, if we multiply this and this, we get the green guy, and the rest follows as well. So that's where we get this matrix of the big X matrix of eigenvalues and the matrix of the eigenvector. So this matrix of eigenvalue, and this is a matrix of the eigen. Did I just say eigenvalue? I always get mixed up between them, but these eigenvalues, because this is the capital of lambda, so small lambda and capital lambda. Okay, eigenvalues, and these are eigenvector. Okay, so that's actually the first part, and actually the second part is, well, since you get this formula right here, you can play around with it. We can put the inverse of the x in here or in here, so we can evaluate this term in terms of the a or in terms of the x, or even in the terms of lambda. So usually I didn't write that here in terms of lambda, but let me show you quickly. So you can either have let's write this down. You can either have this x inverse here, so you have x inverse here x as well, so you will end up with a equal to the x, this should be lambda, right? My bad. So lambda and then x inverse, so you will end up with this formula, or you can also express a lambda in terms of the rest. So you will have let's write that down again. Okay, and right now you put the x in this side, so you have it here, so you can have cool. So you will have this form of eigenvalues, matrix of eigenvalues. And then why does this guy is really powerful? Why knowing that eigenvalues and the eigenvector becomes really powerful? It's when we want to know what happens if we power the matrix. What happens to this system? What is the result of powering the matrix? So what do I mean? So let's take an example of a squared. So what will that be in this term? So we have the x lambda x inverse, that's the first a, but we have another a, right? So we have x big lambda x inverse, and this is just get mushed together into the identity, so that doesn't matter. So in the end I have the square of it, and it's actually pretty simple. So this is, I mean, squaring some diagonal matrix. So this could translate as well to just squaring the inside of those, because these are diagonal, you don't have 0 in it. So this is pretty easy to compute and pretty fast as well. So there's actually the powerful formula here. So what I write here, so we get the formula of a to the power of k equal to the x big lambda k to the x inverse. There you have it. Okay, and my third point is so we see that exactly what matters is just this matrix, right? The matrix of eigenvalues that determines how is the value of the matrix A, how the matrix A will be in the end. So another important point from the book is that what happens if the a of k to the power of k becomes 0. So this is called the stable system. When does the system or the matrix of A become stable? So this happens, as k goes to the infinity, this matrix A goes to a stability when the eigenvalues, all of them, so I eigenvalues is smaller than 1, which means it is 0.00 something, or even can be minus number, because by then you will have that you square them and then you power them to the something really big and it gets to 0, and eventually the system will go to 0 as well. So that is it for the first part of lecture 22 review. So thank you.